Here's another example. So what I'm going to do is I'm going to say, in this course, people will get an A, B, C, or D. And let's say, you all seem like smart people, so let's say the probability of getting an A is 1/2. Half of you would get an A. Probability of getting a B is, let's say, 1/4. Probability of getting a C is 1/8. And the probability of getting a D is 1/8. So, can anyone suggest a very simple way to encode those 4 letters in binary? Well, the most obvious one is this. So how many bits do I need to encode those per letter? 2. 2 bits per grade. Okay, now I'm going to propose the following. Instead of that, we're going to encode it like this. An A, I'm just going to have a single 1. A B, I'm going to have a 0, 1. A C, I'm going to have, actually no, I'm sorry, this is backwards. It doesn't matter, but I prefer to do it this way. An A is a 0, a B is a 1, 0, a C is a 1, 1, 0, and a D is a 1, 1, 1. So, what is the average number of bits per grade over here? So, here I have 1 bit, and that occurs 1/2 the time. Here I have 2 bits, and that occurs 1/4 of the time. Here I have 3 bits, and that occurs 1/8 of the time. And here I have 3 bits, and that occurs 1/8 of the time. So basically I have 1/2 plus 1/4 plus 3/8 plus 3/8, which is, if I translate that all into 8s, it's 4 plus 2 plus 3 plus 3 over 8, which is equal to, okay, 4 plus 2 is 6, plus 3 is 9, plus 3 is 12, that's 12 over 8, which is equal to 1.5 bits per grade. So, this is the naive way, this is the compressed way. So what did I do?
So basically you assign less bits for something that's more probable.
Exactly, and that makes sense, right? Because
But why can't you just use like 1 for B and 1, 0 for C and 1, 1 for D?
great question.
Did you compress it even further, right? 1, 0 and 1, 1 for D. That's how
What happens if I see this?
we're talking about.
Right? Is that B, A, or is it C? So, that's an excellent question. This code, it turns out, has something called the prefix property. Where there's no code word that's the prefix of any other code word. So in other words, there's no code that starts with 0. There's no code that starts, there's no word that starts with 0. There's no word that starts with 1, 0. There's no word that starts with 1, 1, 0, and so on. So in other words, it's impossible to get confused, because if you see the beginning of a code word, you can't possibly confuse it with any other code word. So the point that I'm trying to make here is the following. There does exist a shortest possible description. Of a source. that is called the entropy. This is not, it's related to, but not the same as this is information theoretic entropy, which is similar to, but not the same as thermodynamic entropy. The definition of information theoretic entropy is the following. So if X is a source, H of X, the entropy of X, is equal to the sum over all X times the probability, sum over all possible outcomes of X, probability of that outcome times log base 2 of 1 over the probability of that outcome. And that is the shortest possible description in bits. So over here, what is the entropy of this source? This is Shannon's, the founder of information theory is a guy named Claude Shannon. He proved this, he proved that this is true. So this is not a heuristic, it's actually, you mathematically cannot do any better than that. We are not going to prove this theorem, but if you go on to grad school, you can take a course in information theory, and these kinds of theorems will be proved in detail. So, for this source, what is the entropy? It is sum over X, probability of X, times log 2, 1 over probability of X, which is equal to, okay, X is, excuse me, A, B, C, D. Probability of A is 1/2, so that's 1/2 log base 2 of 1 over 1/2 plus 1/4 log base 2 of 1 over 1/4 plus 1/8 log base 2 of 1 over 1/8 plus 1/4, excuse me, 1/8 log base 2 of 1 over 1/8. What is this? What's 1 over 1/2? 2. So log 2 of that is 1. So this is 1/2. What is log 2 of 1 over 1/4? That's yeah, it'll end up as 1/2. So log 2 of 1 over 1/4 is 2. So that's 2 over 4, which is 1/2. Log 2 of 1 over 1 over 8 is 3. So that's 3 over 8. And this is also 3 over 8. And if you add all of those up, it's 1.5. So in other words, I have a code that does that. The entropy is 1.5. So therefore, there does not exist, this is the best possible code. You cannot compress any more than that. You cannot compress any more than that and not lose information. Any questions? So, next time we're going to look at what's called the Huffman code, which is a way to construct codes like this. The Huffman code is the best. Excuse me, the Huffman code will find an entropy achieving code if one exists. So, we will see you on Thursday. So yeah, this should have been 2. And then this is 4. And then we get 3/4. And this is also the same thing. 1/2 plus 2 over 4 plus 3/4, and that's 1 3/4. Yeah, so 1 3/4 here.